Hi AP. In this video, we're going to look at calculating the pH of a mixture of acids. So yesterday in our video, or in the last video, we talked about looking at the pH of just one acid. But what do we do if there's multiple acids mixed together, or there's more of a solution of a mixture than just one acid in there? So the way that we can decide which acid is going to dominate or be the biggest producer of hydrogen ions is to look at the Ka values of our different acids. So the one with the larger Ka value is going to be the stronger acid and is the one that's going to dominate the production of hydrogen ions. So of the following, HCN, so hydrocyanic acid, HNO2, which is nitrous acid, and water, which of these three is going to dominate or be the biggest producer of hydrogen ions? When we look at their Ka values, we can see HCN is to the negative 10, HNO2 is to negative 4, and water is to negative 14. Because HNO2, or nitrous acid, has the largest Ka value, that one is going to be, of these, the strongest acid. And we talked about the definition of strong in an acid means that more hydrogen ions are going to come off in solution. So more dissociation of our hydrogen ions in our solution. So in our practice problems, we're going to do a lot of math today. In our practice problems, we're going to calculate the pH of a solution, and it's a solution of 1 molar hydrocyanic acid and 5 molar nitrous acid. Now, the one that we're going to look at first, our dominant producer of hydrogen ions, is the one that is the stronger acid. So of the two, the one that's a stronger acid is our nitrous acid. Now, we're not choosing this because of the higher concentration. We're choosing it because it has the higher Ka value. So more hydrogen ions are going to come off in solution. So I'm going to set up to see, well, how many hydrogen ions are going to come off in solution, which is going to cause my pH of my solution to be measured. So we could continue writing these by being in water and showing hydronium and our anion. But at this point, we know that this really breaks apart into its two ions. So our two ions are our hydrogen ion and our nitrite ion, or NO2. And we are in equilibrium. This is a weak acid. I know it's a weak acid because I can see it has a small Ka value in terms of strong versus weak acids. We'll also see it listed on our chart of Ka values. And it's in equilibrium, and I'm given initial concentration of 5.0 molar, and then it hasn't dissolved yet or dissociated yet, so those are 0. I make my ice chart. Minus x, these are all 1 to 1, so plus x, 5 minus x, x, and x. Just like before, these are weak acids, so the amount that our concentration changes is insignificant. So we can ignore that x. Again, our Ka value we've been given, 4.0 times 10 to the negative 4. Remember that our K equation is just the same that we've been doing. Products of reactants raise their coefficients. So we've got our hydrogen ions by our nitrite ions, and then our nitrous acid. So we go ahead and plug in. Got x and x, so we've got x squared on top, and then 5 on the bottom. When I solve for x, I get x to be 0.0447, and that we would plug in for a concentration of our nitrite and our hydrogen ion. So our hydrogen ion concentration, 0.0447 molar. Remember that from hydrogen ion concentration, I can get hydroxide, or from hydrogen ion concentration, I can get pH, because my pH is the negative log of my hydrogen ion concentration. And when I do that, I get a pH of 1.35. And we can see that, and we'll prove this down here, that the contribution of hydrogen ions from hydrocyanic acid is insignificant compared to those produced here. So our dominant pH, so the pH of our solution is 1.35. So pretty acidic solution here. But what if we were also asked to figure out the concentration of our cyanide ions, or the concentration of hydrogen ions from being contributed from our other acid? We would treat this like a common ion problem. So just like we've done in our previous unit on equilibrium. So we've got our HCN also in solution, breaks down into its hydrogen ions and our cyanide ions. We are saying that we are starting with a 1 molar solution. And we know that there's a common ion of hydrogen ions in our solution that we've just calculated up here. So this is our common ion. So this is what we start with for our hydrogen ion concentration. And we haven't dissociated any cyanide ions yet. Again, we shift to make more. So 1 minus x, 0.0447 plus x, and x. Now, we will see that both of these changes are insignificant. And if you don't believe me, we'll do the math and we'll prove it. But this is pretty small, this change. So we're going to, for sake of math, we're going to ignore these when we are calculating for x. So our Ka, again, given to us up top, 4 times 10 to the negative 4. Our Ka equation, H plus Cn minus HCN. So we go ahead and plug in. And we've got 0.0447 x and 1. So when I solve for x here, I get x to be 1.38 times 10 to the negative 9. Well, if I were to, in my calculator, plug in that as the change for my hydrogen ion concentration, because that's x, it's my change, clear all this out, 0.0447 plus 1.38 times 10 to negative 9. Yeah, it's basically the same number of 0.0447, right? I have all these zeros, and then 1, this would be 138. And if I could continue going on, if I had more decimal places on my calculator, but we can see that it's insignificant. So that means that my concentration of cyanide ions is super small, times 10 to the negative 9 molar, and my hydrogen ion concentration is really the same because I don't have a significant contribution of hydrogen ions from my hydrocyanic acid. So it stays the same. So that's why, because our Ka value so much bigger for our nitrous acid, it dominates the hydrogen ion concentration. And so that's why I choose to look at my stronger acid to figure out my pH of my solution as opposed to the weaker acid. It just doesn't produce enough hydrogen ions to make a significant contribution. So that's how we can figure out pH of multiple acids mixed together. We look to see what's stronger. What about an acid that has multiple acidic hydrogens? Well, those are called polyprotic acid. Polyprotic, multiple protons. So these are acids with more than one acidic hydrogen. Okay, so something like carbonic acid. Carbonic acid is H2CO3, so 2 hydrogens on our carbonate. And what happens is that as this dissolves in solution or dissociates, first one hydrogen pops off. So one acidic hydrogen pops off into solution. I have my hydrogen ions, and then remember that has a positive charge. So then if I lose it, I'm going to get a negative charge on what's left because I've lost a hydrogen ion. So now I have just one hydrogen left here. And then that hydrogen can also, then another equation, this hydrogen can also pop off and dissociate. And then I'm just left with my carbonate ion here. And we can see that for this first one, our Ka of my first hydrogen popping off is 4.3 times 10 to the negative 7. For my second hydrogen popping off, so my Ka2, it's 5.6 times 10 to the negative 11. And we can see that this one is much smaller. And we just saw in the previous problem that if my Ka value is much smaller, well, it's really not going to make a significant contribution to those hydrogen ions. But we're going to prove that here by looking at our phosphoric acid. But for all polyprotic acids, the Ka value for that first hydrogen breaking off is going to be much larger than the subsequent ones that come after it. So to figure out, well, what is the change in pH as each of those hydrogens pop off or dissociate from our acid, let's look at phosphoric acid. So phosphoric acid, H3PO4. I'm going to start with a 5 molar solution, and I'm going to figure out the equilibrium concentrations of phosphoric acid, then phosphoric acid without one hydrogen, without two hydrogens, and then just my phosphate ion. So for each of these, we are going to have to write an ice chart because each of these is in equilibrium with starting initial concentrations. It continues to dissociate, and then we want to know equilibrium concentrations. So starting with our H3PO4, our standard phosphoric acid, it's going to break apart into a hydrogen ion and then H2PO4 minus 1. Phosphoric acid, we need to know its Ka value. So we go to our chart and we see phosphoric acid here, H3PO4, has a Ka of 7.5 times 10 to the negative 3. Then we want the next one. So when it's lost one, we have H2PO4, its Ka value. And then finally, when it loses the next one, monohydrogen phosphate ion acid here, and then its Ka value. We can see those Ka values have gotten smaller every time. So that's where I'm pulling my Ka values. You could also look them up if you didn't have a chart. So for this guy, my Ka, 7.5 times 10 to the negative 3. So we're starting with a 5 molar solution of our H3PO4 phosphoric acid, and nothing's dissociated yet. Minus X, X and X. And per usual, weak acid, so therefore this is insignificant. All right, our equation at H plus, H2PO4 minus, all over H3PO4. So we go ahead and plug in. Let's try this. Make sure I've got enough room here. So we've got 7.5 times 10 to the negative 3 equals essentially x squared on the top and 5 on the bottom. So we find that x is equal to 0.194. And that is my hydrogen ion concentration and my concentration of H2PO4. So here I've got my hydrogen ion concentration, 0.194, which I want to know pH as well. So what's my pH to start? Negative log of that, and I get a pH of 0.71. Okay, so that is my first hydrogen's popped off. Now I've got a solution. My second solution, I've got H2PO4 minus hanging out in my solution. It's going to lose a hydrogen ion, and then I'm going to have HPO4 minus 2. Well, we said that my current concentration of H2PO4 is my 0.194 molar, as is my concentration currently in my solution of hydrogen ions. And I haven't dissociated off to any HPO4 minus 2 ions. So again, minus X plus X plus X. And just like last time, these X's are going to be insignificant, and we'll prove that again. So I'll show you when we figure out what X is, we'll add it to this and we'll see, yep, that's pretty darn small. So for this one, and according to our chart, our Ka value, 6.2 times 10 to the negative 8. So Ka is H plus, H2, H2PO4 minus 1. So plugging in 6.2 times 10 to the minus 8. So those cancel out. So X in this case is equal to the Ka value, 6.2 times 10 to the minus 8. So then that means that is our concentration of HPO4 minus 2, which is something we're asked to find. I guess we're also asked to find this guy up here, which we did. So this one, 6.2 times 10 to the negative 8. So that's the change in X. If I were to plug that in here, my 0.194 plus 6.2 times 10 to the minus 8. Again, 0.194, 0.00062. So it really doesn't seem to make a change in terms of concentration. What about pH though? Because that is, right, that is the concentration of hydrogen ions. So the negative log of that would be my pH, but that means my pH is still 0.71. So still at this point, my pH is still 0.71 because my hydrogen ion concentration really has no change. If I wanted to, I could write 0.194, 0.0000062. But when we took the negative log of that, we still got a pH of 0.71. Let's see, does that third hydrogen ion coming off make any other impact? So HPO4 minus 2 is going to lose its last hydrogen ion and then just become a phosphate ion. We have HPO4 solution is at 6.2 times 10 to the negative 8. That's needs units. And then my hydrogen ion solution is this guy still here, 0.194, and nothing here. Again, minus X, X and X. 6.2, 10 to the minus 8 minus X. And the Ka value of this weak acid, according to our chart, 2.2 times 10 to the negative 13. So, 10 to the 5th smaller here. Again, Ka, H plus, PO4 minus 3, HPO4 minus 2. We plug in all of these. I think you'll take my word for it that when we get to this point, our X equals 7.03 times 10 to the negative 20. That's tiny, even smaller. So that is my concentration of phosphate ions, 7.03 times 10 to the negative 20 molar. Okay, so I have found that. So I've checked off each of these. Okay, so that's good. But if I were to add this to even this number, so I'm at 8, I'd have 12 more places, or 9 more places, and then 703, right? Tiny changes. So again, my pH, even at this point, does not change. It's still 0.71. So all of this to say, the first acidic hydrogen that breaks off or that dissociates is the only significant contribution to the hydrogen ion concentration in solution and the overall pH of the solution. SOLUN is a shorthand version for solution. So all of this to prove and say we really only have to do the first one. So if I said, well, what's the pH of 1 molar carbonic acid? Well, you'd look and see carbonic acid, H2CO3, is a weak acid. We can find it on our chart, I think. Yep. On our chart here, 4.3 times 10 to the negative 7 is its Ka value. And polyprotic acid, we can lose multiple hydrogens. But we know we only care about that first one. It's the only one that matters. So I'm just going to care about the first one, HCO3 minus. We set our Ka value 4.3 times 10 to the negative 7. I have a 1 molar solution of it. It has not dissociated yet. XXX, 1 minus X, X, X. And weak acid, so this amount of dissociation to its change, basically insignificant, so we can ignore it. Ka is H plus. HCO3, you guys should be pros at these by now. HCO3, and I plug in 4.3 times 10 to the negative 7. H plus is X, and X, so I get X squared, and then 1 on the bottom, which means when I do all my solving, I find that my X is equal to 6.56 times 10 to the negative 4. And that is equal to my HCO3 concentration and my H plus. So my H plus concentration, hydrogen ion concentration, 6.56 times 10 to the negative 4 molar. When I take the negative log of that, I get a pH equal to 3.18. We could go through and say, well, now we dissociate off another hydrogen ion. And we could say that this is our starting concentration. And we could say that this one is. Or you could say, you know what? This we just proved up here is insignificant. So we don't have to. And we can just say that, you know what? The only one that really matters is the first one. And the pH is 3.18. So that is the pH of our solution. So we'll continue to practice that in class, and you'll be pros by the end.